Welcome to qnawire.
What is the average distance between nitrogen molecules at standard temperature pressure? So we are going to start off from the ideal gas law. So pressure times volume, so PV is equal to number of molecules, Boltzmann gas constant times temperature. And we're going to rearrange this so that we get volume divided by, the number of molecules divided by the volume, so the number of molecules per volume. So if you like, the density of molecules, so number of molecules per volume is equal to pressure over Boltzmann gas constant and temperature. We're going to assume in this that the space occupied by the nitrogen molecules is minuscule. I mean, this is inherent in the ideal gas law. If we wanted to correct this, we could use the van der Waals correction, but it won't actually make that much of a difference. And besides, this hasn't been covered in the book at this point. But that's what we're assuming. So we take standard temperature pressure. So standard pressure, so P is equal to 1.013 times 10 to the 5 pascals. Boltzmann gas constant is equal to 1.38 times 10 to the minus 23. And we are taking the temperature to be absolute zero, which is 273 Kelvin. Sorry, not absolute zero. We're taking it to be 0 degrees Celsius, which is 273 degrees Celsius because standard temperature pressure. And substituting all of those in, we get number of molecules per volume. N over V is equal to 2.68 times 10 to the 25 molecules per meter cubed. So just meters. Let's just correct that. So meters cubed. Per meters cubed. So this number of molecules per meters cubed is equal to this number here. And so we want to get this in terms of molecules per meter, and then 1 divided by that. So what we really want is, so what we're going to do is we're going to take 1 over the cube root of this number will give us the average distance between each molecule. Because if you think about this on a 3D grid, and then that gives you the separation in 3 dimensions, we just want the separation in 1 dimension. So we're going to just take the cubic root. So we want to find the average meter separation as opposed to per meter cube separation. So that's thinking about this in terms of dimensional analysis. Dist is equal to 1 divided by the cubic root of 2.68 times 10 to the 25, which gives us 3.34 times 10 to the minus 9 meters per molecule. Or actually, we don't need the second because we're specifying that it's distance per molecule anyway. So the average separation per molecule is 3.34 times 10 to the minus 9 meters.